Mathematics and Computer Science of Idanova University of Technology in 2011. He worked as a postdoctoral researcher at the Information Technology of Academia Sincere. He then joined the Radboud University and is currently the research group leader and professor at the university. Peter has published extensively in accelerating crypto software. His initial works on AES is quite famous, as well as accelerating cryptanalysis. More recently, he works on post-quantum crypto, has authored the post-quantum crypto ciphers New Hope and NTRU HRSS. So these are key-based encapsulation schemes which are used in post-quantum PLS experiments by Google. So over to you, Peter.
All right, thank you very much. Let me start sharing my screen, my slides here. Do you all see the slides? Does that work? Someone say yes.
Yeah, it's
yes.
Okay, perfect. Thank you very much. Yeah, thank you very much for inviting me. As already last year, I think it's a huge pity that I can't be in India right now. I would very much prefer to be in somewhat warm India than in rather gray and coldish Netherlands right now. But it is as it is. So the thought for this tutorial was that maybe some of you have attended my tutorial last year at Space, which was on lattice-based chems. And I thought, okay, so as we've covered chems last year, let's go for signatures this year. And then, well, I think the maybe most interesting realm of post-quantum signatures is hash-based signatures, because the basic principles are very easy to understand. You can explain them essentially on a beer coaster. You'll see in a moment what I mean. And then, well, over the years, they became more and more refined, and more tricks and tweaks got added to it. So the setup is same as last year. As I mentioned already, my idea is to give a lecture of roughly an hour, maybe a little bit more than an hour. And then afterwards, I have a programming exercise for you. So the programming exercise will be to implement some very simple hash-based signature scheme. Actually, two schemes that I'll also be covering in the talk. And well, you can program that. You can ask questions in Slack. I'll do my very best to help you and answer the questions in Slack. And then at the very end, I'll show what some solution to this programming exercise could look like. All right, let's get started. So when you look at post-quantum crypto, and maybe you can specifically look at the NIST post-quantum competition, but it doesn't even matter so much. All the signatures, they have one thing in common, and that is that they need a hash function. So some good cryptographic hash function without going into too much detail of what properties each scheme requires from it. And in this talk, we're going to look at what we can do if we have just a hash function. Now, as a reminder for everyone, hash functions, well, they take long strings and map them, or potentially arbitrarily long strings, and map them to fixed length strings. And there's these three properties that you learn in your Crypto 101 lecture on what every good cryptographic hash function should have. That's collision resistance, which means it's hard to find two inputs mapping to the same output. Now, obviously, there are, if you actually admit arbitrarily long strings as input, and if you map to strings of fixed length output, there is infinitely many strings that map to the same output, but it should be hard to find those. And then there's preimage resistance, so that when you're given an output, it's hard to find an input mapping to that output. And then there is second preimage resistance, which is that you're given an input and an output, and it's hard to find a second input. Now, the collision resistance, the assumption that a function is collision resistant, is much stronger than preimage and second preimage resistance. So ideally, when building something out of hash functions, we would want to not rely on collision resistance. And we will see that, to some extent, we can actually do this. Okay, so let's take first example. First example is a rather boring construction. It's signatures for 0-bit messages. And you might be wondering, well, what's a 0-bit message? Nice example of this that at least I think is quite useful is communication between the airbag in a car and the sensor triggering that airbag. So just imagine that, well, you have the sensor sitting in front of the car, and when the car hits something, that sensor detects that and notifies the explosive charge in the airbag to go boom, right? And it doesn't say, you know, boom today, boom tomorrow. It just says boom, and that's a 0-bit message. The whole information in that message is in the point in time when it's being sent, namely, well, boom, as soon as possible. Now, we kind of would imagine, at least for the moment, that we want this message to be cryptographically secured, as in we don't want the explosive charge to be, well, receive forged boom messages and then just go boom while you're driving. Another example for a 0-bit message is a more funny example. Maybe some of you know that there was the app on Android and iOS called Yo, where you could send to people in your contact list just Yo, nothing else. And at first, when it appeared in the app markets, Apple thought that it's just a joke. They didn't admit it. But then later, it turned out that not only was it not really a joke, but it was mildly successful. And while you could just communicate with your friends and peers by just sending Yo. Okay, so how would we construct a signature scheme for such a 0-bit message? Well, we take a random string, say 256 bits, and we hash that string. Now, the random string that we generated at the beginning is our secret key, and the hash of it is our public key. And then when we want to sign, we just send the secret key. And verification means, well, we just take that secret key, we hash it, and we check if it matches the public key. It's a rather straightforward scheme. Question would be, can we construct a security reduction for that scheme? It turns out we can. We would want to reduce from pre-image resistance here. And clearly an attacker who can compute pre-images and has the public key can break the scheme, right? They can recover the secret key, send the secret key, and make the airbag go boom. But can we go the other way around? Can we take a forgery of this signature as an oracle that produces us a pre-image? And we can. So we assume they have this oracle that computes a forgery given a public key. And now what we want to do is we get some input y, and we want to compute a pre-image to this input y. So what we do is we just program this input into the public key, and then the oracle will compute a pre-image, because that's what it means to actually forge a signature here. Or will it? Well, there's one tiny gap in this proof. Actually a bit tricky. Can anyone tell what this problem in the proof might be? If you have an idea, just unmute yourself and speak. Why would the oracle here not be giving us the pre-image? Yeah, this interactive setting never works very well over Zoom, and I can't even see you. Okay, I will tell you. The problem is that the string y that we try to invert that we want to get the pre-image of is not necessarily the output of a hash function, of the hash function h. So if this oracle can distinguish between some random string and the output of the hash function, then it might not work, right? The oracle has a fair deal of saying, well, if you give me a not proper public key, then I'm not forging. I'm not actually inverting this. So what we require additionally for this proof is that the hash function has a property called undetectability, so that an attacker can't tell if a string of the right length, a bit string of the right length, is the output of a hash function or is just, well, a random bit string. From now on, through the rest of the talk, we'll assume that all hash functions are undetectable. Okay, let's do something more interesting. Let's actually sign 1-bit messages. So this is where it's not so hard anymore to find examples where you might want this. So just imagine an election where you need to say yes or no. For a while, when giving this talk or giving this example, I was giving the Brexit vote as an example here, where you want to vote if you want to stay within the European Union or not, and it's just a yes or no decision. So what we do in order to sign 1-bit messages is we generate 256-bit random values R0 and R1. So now we have 2 such strings, and we hash each of them individually. So we compute h of R0, we compute h of R1, and this pair is going to be our public key. And now when we want to sign, we just reveal the corresponding part of our secret key. By the way, when I'm sometimes interrupting this, it's because there's messages popping up here of people who are in the waiting room, and I'm clicking then on admit to admit them. I don't know how to what to do about this. So anyway, there's constantly people popping up here who want to be admitted. All right, so we're basically just revealing half of our secret key, and then the verification just checks if, well, we revealed the right thing, right? So if we wanted to sign the message 0, did we reveal R0? If we want to sign the message 1, did we reveal R1? So again, the verification is just hashing and checking if it corresponds to the right part of the public key. Let's look at the security reduction for this. So idea is the same. We again want to reduce from pre-image resistance. We again will just put our challenge that we want to invert into the public key. And now we have 2 options. We can either put it in the first component of the public key or in the second component of the public key. Now, this is a one-time signature scheme, which means that the attacker is actually allowed, or the oracle, this attack oracle, the forgery oracle, is allowed to query us and get 1 signature on a message, and is then supposed to give us the signature on another message. So it can ask us for the signature on 0, and then the forgery would be to give us the signature on 1, or the other way around. And now we have a bit of a problem, because the oracle may ask us for the signature of the value that we don't know the pre-image for. So in other words, it asks us for a signature of a message that we can't sign. That will happen with probability 1/2, right? With probably 1/2, the oracle just chooses exactly the component of our public key that we programmed to contain the challenge. But if we can answer this, then afterwards A will forge and will exactly return the pre-image for the other component, which is exactly where we put our challenge. So that's great. Now we see here that this reduction works only with a probability of 1/2, because in 1/2 of the cases we just don't know how to answer the query by the oracle. So we have a tightness loss here of 1/2. Keep that in mind for later. Okay, so now let's do something actually interesting. Let's sign 256-bit messages. And if we can do that, then, well, we can sign hashes of messages, which is a pretty good way of signing arbitrary messages, pretty much. And we'll get back to why we wouldn't want to do that directly. But for the moment, let's just assume 256-bit signing is just enough. So we do this by generating 512 random values, each of 256 bits, and they're called R00, R01, R10, R11, and so on, up to R2550, R2551. So in other words, for each of the 256 bits that we want to sign, we generate 2 random values. And while we hash all of these 512 values individually, so the hash of R00, hash of R01, and so on. That's our public key. And you may already see where this is going. So in order to sign a message of bits B0 to B255, we look at the values of this message and the individual bits. And for each bit, we reveal either the 0 component of our secret key or the 1 component of our secret key. So in other words, we reveal R0, B0, R1, B1, R2, B2, and so on up to R255, B255. verification is, well, you go through the message, you take each individual bit, take the corresponding public key component, and signature, well, you take the signature component that you get, you hash it, and you compare it to the corresponding public key component. This is a one-time signature scheme still, because imagine that you've signed 2 messages with this, 2 different messages. Then at least in one position, you've revealed both components of the secret key. And if you've done this in a few positions, then you can trivially forge by just, well, using different combinations of bits where, well, both components of the secret key have been revealed. So we can sign just one message once with this. That's quite a limitation, and we're going to look at this limitation in a bit. But for now, let's just accept it's a one-time signature scheme. It's actually the Lamport one-time signature scheme. And the task of the first programming task in the second part of this tutorial will be to implement this Lamport signature scheme. Let's first look at the security. Let's again reduce this from pre-image resistance of the hash function. So again, the idea is the same as before. We get our value y that we would like to invert, and we put it somewhere in the public key. Now we have 512 positions in the public key. We just pick one at random. And now the attacker asks for the one signature that the attacker or this oracle is allowed to ask. And with probability 1/2, we can't give it, because with probability 1/2, in this position where we placed y, the attacker is choosing exactly the bit that we replaced y by. So again, a 1/2 tightness loss there, but then it continues. So now the attacker forges. And that means that the attacker has to flip at least one bit in the message that he saw before. And now we have a chance in 1/256 that the attacker flips the bit where we have the challenge. So the overall tightness loss here is 1/256 times 1/2, which is 1 divided by 512. So we're actually losing 9 bits of tightness here, because we have, well, 2 to the 9 hashes in total. And we just don't know which one of the attacker, which one of those the attack oracle, the forgery oracle, is going to invert. Again, something to keep in mind. We will get back to this later. Okay, so this is Lamport signatures, one-time signatures. They work just fine. And as I said, we're going to implement them in the second part of the tutorial. The somewhat nasty bit about Lamport signatures is that they're rather big. So we have in the signature 256 values of 256 bits each, which is 8 kilobytes, which is, well, quite big. And the question is if we can somehow make them smaller. Well, for example, by trading off speed for size. And we can. And the idea here is that we don't just take a random string and we hash it once, but we hash it multiple times. So we basically compute a chain of hashes. On the next slide, I'll have a picture for this. Now, when we do this, let's work with concrete values here. We take our 256-bit string, and instead of generating 512 random values, we only generate 64 random values, each of 256 bits. And then instead of hashing each of them just once, we hash each of them 15 times. So we compute h to the 15 of R0, h to the 15 of R1, and so on, up to h to the 15 of R63. That's going to be our public. Now for signing, we chop our message, our 256-bit message, not in bits, but we chop it into blocks of 4 bits each. And now we sign sort of each of these blocks individually by taking the 4-bit value as an index into that hash chain that we computed before. So, for example, if the first block is first 4-bit block as an integer is 7, then we would compute h to the 7 of R0 of that secret input value. And then if the next block is 0, we would actually reveal R1. And if the next one is, say, 12, we would compute h to the 12 of R2, and so on. That's going to be our signature. What does verification do? Well, verification just takes these chains and computes them all the way to the top. So it computes basically the remaining bits of the chain and then compares to the public key that we revealed before. So in other words, we're taking h to the 15 minus m0, h to the 15 minus m1, and so on, of the components of the signature that we received. This is what a picture looks like. So we have these 64 chains that start with secret random values, and we hash them up, and then in the white boxes up here, we see the public key up here. And the signature is basically, well, some intermediate values in these chains. Looks great, doesn't work. Well, doesn't work straight away, because this is terribly insecure. This is not very hard to see. Just assume that we have some message that is being signed that in the first component has 8, could well be. Then, well, the attacker can go upwards. I mean, that's actually exactly what you're doing in verification. You're continuing these chains. So now the attacker can just choose 9 in the first component, or 10, or 11, or anything. So basically, the attacker can sign messages that in each of the component are bigger than the one message that the attacker queried before. Now we can solve that. And the idea is that, well, because we know that the attacker can go up in chains efficiently, we force an attacker to go down in another chain. So whenever you're going up in one chain, you need to go down in another chain. And that's exactly what an attacker cannot do. How do we do this? Well, we just take all of these integers indicated by these 4-bit chunks. We add them all up, and we subtract them from the maximum value that you could get. Now we have 64 times 15. That's the maximum value. That is 960. So we're taking 960 minus all the sum over all of these mi when we're signing. And we get a value here that is obviously between 0 and 960. So that we chop again into blocks of 4 bits each. And we write it in radix 16, and then we get C0, C1, and C2, so as 4-bit chunks. And then we compute hash chains for those as well. So we also generate 3 additional random secret values, well, R64, R65, and R66. And then we just hash up to these positions of C. And now, whenever any of these MIs becomes bigger, at least one of the CIs becomes smaller, and then, well, the attacker would need to go down the chain. So in total, what we're getting is 67 hash chains, which means that the signatures have slightly more than 2 kilobytes. So we increased the number of hashes quite a bit compared to Lamport, but also, well, our signatures are only about 1/4 of the size, roughly. A bit more, actually. The bit more comes from these checksum chains. Several notes about this. So when I introduced this, the example that I used has concrete values. But the value of the length of these chains, so this W equals 16, so 15 hashes per chain, W minus 1, that's tunable. So you could, for example, also say we make chains of length 256, and we chop our message into bytes instead of nibbles. So that means that our signatures become smaller, but it also means that we need to compute way more hashes for signing and for verification. There's lots of trade-offs. So for example, while we had these 2.1 kilobyte signatures before with a W equals 16, we can almost halve this when we're using W equals 256, but signing becomes about 8 times slower. So there is actually this trade-off between speed and size, but when you make the size linearly smaller, you're increasing the running time exponentially, which is an okay trade-off as long as the exponent isn't too big, obviously. But at some point, this becomes extremely unattractive, and for really large values becomes infeasible. Another very nice note, and we're going to use this quite a bit in the following, is that during verification, we recover the public key. So we're actually just recomputing the public key. That was not the case with Lamport, where we're only getting half of the public key back. But here we're recovering the full public key. And that means we can compress the public key. We can just, instead of publishing 67 256-bit values, we can just publish the hash of it. And then verification recovers that public key, hashes it, and then just compares the hashes. Or we can use it in, well, the schemes that we're introducing in a bit to not send the public key around because it's actually recovered as part of verification. Let's first look at a reduction proof here, and that's a bit more nasty. So intuitively, what you need to do in order to forge is you need to go down the chain, which means you need to compute a pre-image or a second pre-image, really. But it's very hard to prove that. Because imagine that you're putting the challenge somewhere in one of these chains. Then when the forgery oracle is producing a forgery, it may either actually give you the pre-image that you want, or some other pre-image, or it may just use a completely different chain that collides further up, that actually never goes through the value that you need. It can just, as long as it collides and results in the same public key component, it's still a valid forgery. So the problem is that this reduction, in this reduction, the forgery oracle gives us either a pre-image or it gives us a collision. And so we really only get a reduction from collision resistance. And that's not something we want, because as I mentioned at the beginning, collision resistance is a much stronger assumption than pre-image or second pre-image resistance. Now, Hülsing in 2013 came up with the idea that if we control one input in this collision, then we get a second pre-image, and then we get a reduction from second pre-images. The way to do this is to use bit masks in the inputs to each of the hash functions. So instead of just hashing up, in each of the layers, you take your random value, you XOR it with a bit mask, and then you hash. And these bit masks, they become part of the public key. So now when I'm placing my challenge somewhere, I can afterwards control through these bit masks if there's a collision exactly which value is colliding. And therefore, I get a reduction from second pre-image resistance. Okay, so now so far, I started with 0-bit messages and 1-bit messages, but we've been signing 256-bit messages so far. That's pretty cool. But if we use those to just sign a message hash, then again, for the message hash, we're relying on collision resistance. Because otherwise, well, somebody could just find two colliding inputs, get a signature on one of them, and then claim that the signature is valid also for the other one, and have a valid forgery. So can we get around this? And the answer is yes, we can. And the way to do this is that instead of just hashing, is we pick a random R, and we compute the hash of R concatenated with M. And then we send R as part of the signature. So that prevents us from, well, if now the attacker asks for two colliding messages, or has two colliding messages in a hash function, it doesn't give him a forgery, because we're randomizing this hash through this R at the beginning. So then it won't collide anymore with the other message, well, at least under reasonable assumptions on the hash function. We can make that deterministic. So what we can do is we can just take out the message M that we want to sign, and we feed it as a public input into a PRF that a secret input has some value S for an S that we just store alongside the secret key. And then we use that as R. And when we do this, then our signature scheme becomes collision resilient. So in other words, we don't rely on collision resistance of the hash function. It's nice. Still, so far, we only had one-time signatures. So we could sign exactly one message, and then afterwards we need to generate a new key pair. Not so exciting. I mean, there's some applications where this is probably just fine, but we would like to be able to generate a key pair and then sign multiple messages with this. And in the late 70s, Merkle showed how to leverage a one-time signature scheme and build a signature scheme that you can use to sign multiple times. And here's the idea. The idea is to use so-called Merkle trees. So we have these one-time signature schemes. You see them at the bottom here at the leaf. So they have these these X values, that's the secret keys. You have the Y values, that's the public keys. And then you have the hashes of the public keys here in the leaves of the tree. And then we just concatenate the hashes of the public keys and we hash them again. And then we concatenate those hashes and we hash again. And then, well, at some point we reach the root of the tree. And the root of the tree is going to be our public key. So that's what we do during key generation. We compute one such tree, publish the root. Now, when we want to sign, let's say we want to sign using, we use the leaves one by one, and we need to remember which leaves we have already used. So let's assume that we want to sign using the second leaf here. So this X001 secret key. Then, well, we just use this one-time signature scheme key pair to sign our message. And then we send the index that we use. So in this case, we send 1. We're sending the signature on the message. We're sending the public key of the one-time signature scheme. And then we send this authentication path. So that's basically always the neighboring hashes that you need to go up in the tree. So this hash we can compute because we included the public key. Then from the authentication path, we get the neighboring hash. So we can concatenate these two to get this one. We again, from the authentication path, get the neighboring hash to go up here. And again, from the authentication path, get the neighboring hash to obtain the public key. And that's what verification does. It verifies the one-time signature and then goes up following, well, this authentication, using the nodes in the authentication path, going up the tree to reconstruct the root and then check that the root is the same that was sent before. So here's, again, what the signature looks like. We have the index I, we have the signature on M using XI, we have our public key YI and the authentication path. And you see here now that YI is in gray. And the reason is that if we're using Winternet's one-time signatures, we don't need to send YI because the verifier reconstructs YI and can then basically just from the signature already get YI, hash it, and then go up in the tree. So we're saving quite a bit of space in this one-time in this multi-time signature here because we don't need to include public keys. However, it's a very, very critical aspect to this, and this is that we have a stateful scheme. We need to remember every time we sign which leaves we have already used for signing. And we come back to that in a bit. So informally, the security of this is that if the one-time signature schemes used at the leaf nodes are existentially unforgeable under chosen message attacks, and we have a collision-resistant hash in the tree, then Merkle signatures are secure. And if we want to get rid of this assumption that the hash function used in the tree is collision-resistant, then we can again use this bit mask trick to control inputs there and also get a reduction from second pre-image resistance. But as I said, Merkle signatures are stateful. We need to remember which leaves we have already used. Okay, so let's think a little bit about efficiency of this whole thing. So when we're generating the key at the beginning, I said we need to compute the whole tree. And if we do this naively, we just, well, we compute the whole tree, put it in memory, and then we're done. The problem is that this needs 2 to the h memory, where h is the height of the tree, and 2 to the h is also the number of leaf nodes. Right? So there is a better approach, and that is called tree hash. And the tree hash basically builds the tree from left to right and keeps nodes on a stack where whenever it can hash upwards, it just hashes upwards and then forgets sort of the left part that it won't ever need anymore. And whenever it can't hash upwards, it builds more nodes from the bottom up so that it can go further upwards and then again forgets the left half that is not needed anymore. So this algorithm, which is, well, just constructing the tree once, like sort of left to right, well, bottom left to the root, and just minimizing memory usage while doing it. With this, we need only h+1 hashes on that stack. So from an exponential memory usage, we go to linear memory usage. So that's quite efficient when computing this in a memory constrained environment. We still have to compute the whole tree. So we still have to compute the 2 to the h hashes. Now, in key generation, we need to compute the whole tree. That's just how it is. We need to get to the root. But how about signing? So maybe we can accept that key generation is rather slow. And well, we do that once, and then we keep the key sitting around. But signing, we would like to be fast. Now, you can think of it as follows. You can say, well, if we don't care about secret key size, we just build the tree once, like with actual memory usage 2 to the 8th, in key generation, we just store it. And then, well, we don't need to compute it during signing anymore because we have it sitting around as part of the secret key. We can also recompute the whole tree every time, which means we don't need that much memory, but it's very, very slow signing. There is also an obvious trade-off that you can keep in mind, and that is to remember the last authentication path. So if you're imagining that you're going from left to right through the leaf nodes and use them one by one, then for every second leaf node that you're using, there's only one node that changes in the authentication path. For every 4th one, there's only 2 that change. For every 8th one, there's only 3 that change, and so on. So most of the time, you can actually reuse most of the nodes. The problem is that if you're doing that, the signing speed largely depends on where you are in your leaf nodes. Basically, the worst situation is when you're crossing from the left half of the tree to the right half of the tree, where you need to recompute the whole authentication path. And basically, that means the whole tree. But you can sort of balance this out and distribute these pre-computations over multiple signatures so that you get almost the same speed for every signature, for every signing, independent of the position. And sort of the very commonly used algorithm there is known as BDS traversal. It's by Buchmann, Dahmen, and Schneider from 2008. And I won't go into the details of that algorithm, but if you're interested, if you actually want to implement it, it's in the paper Merkle Tree Traversal Revisited, and there's a link. You also find it in for example, the reference implementation of XMSS, the extended Merkle signature scheme, which is by now standardized. Okay, so what is the downside of these stateful signature schemes? You would think, I mean, counting 1, 2, 3, like which leaf nodes have I already used? This is not so hard. Everybody should be able to just count 1, 2, 3. However, let's just remember that if we fail to count 1, 2, 3, it's a security disaster, because that means you're using the same one-time signature to sign 2 messages. And that basically security is immediately completely down the drain. It's a one-time signature scheme after all. Can it be hard to count 1, 2, 3? Well, just imagine that you have a backup. Imagine that you put your signing key into a backup, which generally is not a terrible idea if you want to keep it around even after the crash of your machine. But now you're restoring your secret key, and you're restoring an old state of the secret key. And you go back to the index of when you created the backup. And then you start again from that index and you sign messages. And all security is lost. Sort of a special case of this would be VM snapshots. If you're often working with snapshots that you're trying out some configuration, maybe do a few signatures, and then at some point realize, now that actually that didn't work very well, let me go back to an older version of the virtual machine. It will also have the old version of the key. It can also be tricky for load balancing. If you have multiple machines signing messages using the same key, you need to do something smart. It can be done with hash-based signatures, but you need to then distribute separate parts of the tree to different machines. If everybody knows the whole tree and they're trying to go one by one through that tree, synchronization issues will be a nightmare. Maybe actually the worst problem is that the API, in both an abstract sense and a very concrete implementation sense, is incompatible. It doesn't even fit the definition of what a cryptographic signature is, that the secret key changes with every signature. However, there's also one advantage to this. You're probably familiar with the notion of forward secrecy, which we have for chems and for encryption. So the idea is that after some key has been compromised, old ciphertexts still remain secure. And we have something somewhat similar for signatures, which is forward security, which means that old signatures still remain valid after a key has been compromised. Now, if we want this, then we need a timestamp really baked into the signature so that when we're saying my key has been compromised, it's very clear that old signatures have been generated before that key compromise, and it wouldn't be possible anymore to regenerate message or signatures that appear as if they were signed before. So that means that the secret key has to evolve to disable signing in the past. If you still had all the information around that you had 2 years ago, then you can also produce all the signatures that you had produced 2 years ago, just, well, maybe on different messages. So for hash-based signatures, this is basically free. If we just generate our one-time signature key pairs at the bottom of the tree as hashes of each other. So we take some random string to generate the first one, and then we hash that to generate the next one. Then we only ever store the next valid one-time signature pair. Everything in the past we can't go back to because, well, it's the output of a hash function. We forgot what we had sitting around. We just need to keep the hashes of the public keys because we need those to reconstruct the tree. But those are not secret, and we can't sign with them. So now, if we do this, then after key compromise, we can just say, well, sorry, my key has been compromised. I was at the following index. And then it's very clear that with that key that was compromised, nobody can be generating signatures at a lower index. And the old signatures remain still valid. Okay, so let's go a little bit beyond that, because you remember that key generation had to compute the whole tree. And that's infeasible for really large trees. So you may imagine an example of, say, height 10. Height 10 means we have 1024 leaf nodes, which means we can sign 1024 messages with one key. That's actually not a lot. But still, we need to compute, well, 1024 leaf nodes at the beginning, one-time signature pairs, hash all of that up during key generation. Now, if you imagine you actually want to sign 2 to the 30, 2 to the 40 messages, you may not be able to even generate the key anymore for this. So here's an idea to solve that. First of all, we're generating all secret keys pseudo-randomly. So we're taking some master secret that we're storing as our secret key. And then we're using a PRF with that secret seed, with that secret master key, and the position in the tree. So we now need to have a way to address every secret in the whole tree that wants to be generated. And now we use a hierarchy of trees. So what we're doing is we compute some tree of a like height, I don't know, maybe 5 or 6, or maybe up to 10, something like that. And then we use the leaf nodes to sign the roots of another tree. So you can think of this as a certification tree, where basically, well, at the very bottom, we have a tree where the leaf nodes are used to sign messages. And on top of that, we're just building this hierarchy of certifications until, well, the real public key of the whole scheme is just the root node of the top tree. And the cool thing is that now key generation needs to generate only the top tree. Because all of this whole hypertree is generated deterministically, and on the fly, only those components that we need for a signature, we never need to compute the full thing. We can come up with trees that are so big that would be completely infeasible to ever compute, because we never actually compute the whole thing. Now, with this in mind, we can go beyond that, and we can actually eliminate the state. And here's a picture that you see of, well, obviously of a swimming pool at a hotel. You see the pyramids of Gizeh in the background. So that was taken after Africa Trip 2013, which was in Egypt. And after that conference, we traveled to the pyramids and we stayed there for some days. And in this pool, we came up with a name for this project, Sphinx, Stateless Practical Hash-Based Signatures. Or actually, if you want a proper acronym, Stateless Practical Hash-Based Incredibly Nice Cryptographic Signatures. So that's the kind of naming you come up with when you're in such a nice pool, in such a nice location. And this is joint work in 2015 with Ben Bernstein, Dara Hopwood, Andreas Hülsing, Tanja Lange, Ruben Niederhagen, Luisa Papakristodolou, Michael Schneider, well, myself, and Suko Volkexahern. What did we do? Well, we took that idea of this hypertree construction that was around before already, And we extended that by saying, okay, at the very bottom, we don't take the one-time signature scheme to sign messages, but we're signing it to sign using it to sign the public key of a few-time signature scheme. What's a few-time signature scheme? Well, it's a signature scheme that you can, as the name suggests, use to sign a few times, 5 times, maybe 6 or 7 times. And the big advantage of doing that is that, well, in order to make the whole thing stateless, the idea is we make a tree really huge, and now we just, every time we want to sign, we just pick a leaf at random. And as long as, you know, we don't collide in the leaves, that's just going to be fine. But if you want to make sure that with one-time signatures at the bottom, you don't ever collide, you need a really, really huge tree. With a few-time signature scheme, you can allow a few collisions as long as the probability for an attacker to forge multiplied after n collisions, multiplied by the probability to have n collisions, is negligible. Careful balancing, but with this, you can get a tree of height only 60 instead of more than 256. So what does a few-time signature scheme look like? Well, remember Lamport, very beginning, 256-bit messages, straightforward design. Lamport reveals half of the secret key with each signature. Now, the idea in Horse was also around already before Sphinx, is to use a much, much bigger secret key and to reveal only a very, very small portion. And then to say, well, when you're using this, you always have to sign the hash of a message, never the hash message itself, so that you can't actually fully, as an attacker, control what you're signing. And then the idea is that even after having seen a few signatures, you will never have sufficiently many components of the secret key to puzzle together a signature for a message where you don't actually fully control that hash. Here's some example parameters. Let's assume we're starting with 2 to the 16 random values. And we're hashing all of them individually. So we compute 2 to the 16 hashes. And then we're signing a 512-bit message hash, G of M. So where we take these 512 bits and we chop them into chunks of 16 bits each. That's 32 chunks, G0 to G31. And each of them is a 16-bit integer. And then we're revealing exactly the secret values that are indexed by those 32 16-bit integers. So we're revealing 32 out of 65,536 secret key values. And then if we're doing this, then even after, say, 5 signatures, the attacker does not know enough secret key to forge with non-negligible probability. Okay, so there's a bit of a problem with Horse, and that is that the public key is pretty huge, because we have these 2 to the 16 chunks, we hash them all individually, so we're ending up with 2 megabytes of public key. And well, in our complete construction, in the Sphinx construction, the public key becomes part of the signature. So that would result in pretty huge signatures. However, what we can do is we can build a hash tree on top of the public key chunk. So basically just yet another Merkle tree, because, well, we don't have enough trees yet. Then we just use the root of the tree as the new public key. And then we include authentication paths again in the signature. Now, if we're implementing that naively, then the size that we're getting for a Horst signature, so Horse with tree, Horst, is we're getting the 32 chunks that we're revealing, each of them 32 bytes. And then we need 32 authentication paths, each of length 16, and each chunk in these authentication paths also of length 32. That's a total of 17,408 bytes. Now, if you're imagining that you're putting 32 authentication paths through the same tree, then on top, all of those authentication paths will collide. So basically, we're sending the same nodes over and over again. So we can optimize there a little bit. And somewhat optimized version, which just at some point sends a whole layer of the tree so that we can, from there, always go completely up, is 1300 and 312 bytes. Okay. So let's look at a concrete instantiation of the whole thing. So we put together an instantiation called Sphinx 256, designed for 128 bits of post-quantum security. We're supporting 2 to the 50 signatures under the same key. Afterwards, security slowly goes down below 128 bits. And we have 12 trees of height 5 each. So this hypertree, the total height of 60 with, 12 individual trees to go from the bottom to the top. We have 256-bit hashes in Winternitz and in Horst, and we use a Winternitz parameter of W equals 16. So that's the parameters that we also saw before. We use Horst with exactly the parameters I showed before. So we have the expanded secret key chunks up to 2 megabytes. But then, well, as I said, we built the Merkle tree on top to have a much smaller public key. We take a randomized message hash using Blake 512. So we have these 512 bits. So again, that's more about Horst. And as a PRG, as a pseudo-random generator, we use Cha-Cha-12. Now, what's the cost for signing? It's actually quite a bit because, well, we need to compute the Horst signature, and then we need to compute 12 full trees to go from the bottom up to the top. And in these trees, we need to pseudo-randomly generate, well, each tree has height 5, so there's 32 leaf nodes, so we need to compute 32 times 12 one-time signature pairs for the what signature so that we get the corresponding hashes and can go up to the tree to get the root node. So we have 2 functions that really determine the speed. That's the function f that hashes from 256 to 256 bits. That's basically inside watts where we're hashing up in these chains. And also in the public key generation of Horst, where we take the random values and we hash them once each individually to obtain the 2 to the 16 public values. And then we have the hashing in the trees. And that one always takes, well, 512 bits. So 2 nodes, concatenates them and hashes them upwards to 256 bits. Overall, signing one message requires 451,000 invocations of F and a bit more than 90,000 invocations of H. Now, to make this fast, you can realize that a full hash function would somewhat be overkill, because a hash function takes messages of arbitrary length and maps them to a fixed length string. We don't have messages of arbitrary length. We have messages of either 256 bits or 512 bits. It's quite special, actually. So we came up with a more efficient construction, more lightweight construction that covers this special case. That's based on a permutation pi, where, well, we take, in order to hash a message, we take the message concatenated with a constant, and we permute, and then we just chop off 256 bits. And if we want to hash from 512 to 256 bits, we're doing that whole thing twice. So permute twice. We're using the Cha-Cha-12 permutation for pi, so the same permutation that is also used in our PRG. And that means that all the building blocks throughout the whole construction, they are built from very similar permutations. So HF and the PRG all use the Cha-Cha-12 permutation. The message hash uses Blake, which is also heavily inspired by the Cha-Cha permutation. Putting all of this together, with Sphinx 256, we get 40 kilobytes of signatures. We get a kilobyte of public key, which is mainly the bit masks that we need to get a second pre-image resistance reduction, and 1 kilobyte of private key, which again is mostly bit masks. We really seriously optimized that using AVX instructions, AVX2 instructions. And we're using 8 times parallel hashing. So we're always computing 8 hashes in parallel using the vector instructions. And that gets us down to about 1.6 cycles per byte for H and F for hashing. In total, this means that signing is slightly below 52 million cycles. It's not really fast, but we can generate more than 200 signatures per second on 4 cores of a 3 gigahertz Intel CPU. Actually, quite all right for many applications that don't have to sign a lot of data. Verification, much faster, is less than 1.5 million Haswell cycles. And keygen, as far as I recall, we didn't optimize as much, but it's 3.3 million Haswell cycles. So also not super critical. Now, that was Sphinx. Sphinx was 2015. And then about a year later, NIST said that they would want to have proposals for post-quantum signature schemes submitted, well, yet another year later. So they announced this in 2016, 2017 was the deadline. And so I said, okay, well, obvious thing is to submit Sphinx as a proposal. But then, well, maybe let's look through and see what we can improve. Is there anything that we learned now how to do better? And there's a few things. So maybe you remember at the beginning of the talk, I told you that there is this tightness loss in the proofs because there's many hashes. And if you program one hash that you would like to have inverted by the oracle might just pick another one. So tightness loss. And we have lots of hashes in Sphinx. So we actually do not just get a few bits of tightness loss, we get massive tightness loss. And that tightness loss is not just a proof artifact, it is something that actually you can think of can be exploited in an attack. You can think of an attacker trying to forge as solving one out of many second pre-image challenges, just spread across this whole hypertree. Pre-quantumly trivial attack is you just try all inputs of appropriate size and you win if the output matches any of the challenges, not just one, any of these challenges. So this is a real concern, this tightness loss. There's an idea how to address this, and this idea is that you can just use a different hash function for each of these calls. That sounds pretty scary, but it actually isn't if you think of hash functions as members of a hash function family and just picking through the address of the hash in the tree a member of the hash function family. This was actually proposed in a slightly different context, namely for XMSS by Hülsing, Reinefeld, and Song in 2016. And we decided to adopt this trick in the construction of Sphinx Plus that we then submitted to NIST. So we then went further and said, well, this picking of a random hash function, we can merge this together with, while generating random bit masks into something we call a tweakable hash function. And then in the NIST proposal, we construct these tweakable hashes, once from SHA-256, once from Shake-256, or from Haraka. So we dropped this idea to go for SHA-12 as a permutation. NIST very much likes symmetric crypto to be NIST approved, so that would be SHA-256 and Shake-256. Haraka is special purpose hash function for hash-based signatures that is also extremely high speed. And well, it is high speed if you have AES hardware support. So it's using AES and I instructions on Intel. And it's basically there to showcase how fast the proposal can be if you do have hardware support for hashing. It's another tweak that we did. So I said that in these Sphinx and also Sphinx Plus computation proposals, we need to pick a leaf index at random that we're then using to sign. And we're not actually picking it at random, we're picking it at pseudo-random. And in Sphinx, what we did is we take our long-term secret S, and we take the message M, and we run a PRF on that, and that gives us the index I, and gives us the value R that then we're using to compute the message digest, which we're signing. And then we're including I in the signature. In Sphinx Plus, we're again taking M and S as an input to the PRF, but we only generate R as an output of the PRF. And then we feed R and M again into this message hash, but now we do not only take the digest out that we're signing afterwards, but also the index. So the index gets sort of generated later, and now we're including R in the signature. And what that means is that when verifying, the verifier needs to reconstruct the index I, and the verifier can check that the digest that is being signed and the index I belong together. So the attacker cannot pick D and I independently. The attacker has less freedom to target leaf nodes that, for example, he has already seen many messages in. But he can only do that by playing with messages, and the messages then determine where he ends up. There's more improvements. There is improvements to the few time signature scheme. So instead of using Horst, we're now using something called Force, and yet that is pronounced like the Force in Star Wars. The idea is not to use one big tree on top of a Force public key, but to use multiple smaller instances and have per signature exactly one secret key leaf per tree. So multiple trees, one leaf per tree gets revealed. If you want to know more about this proposal, then we have all of this online on sphinx.org. Now, this is sort of the moment where I would thank you for your attention. And maybe this is actually a good moment to take questions before I'm introducing the programming exercise for the second part of the tutorial. So thank you very much, and let's do questions here. And you can type them in Slack, you can type them here in the chat, or you can just unmute yourself and ask.
Yeah, I think we can wait for some time for the questions.
I can also introduce the exercises, and then you can think of if you have more questions, and then I would assume that there's probably more questions popping up when you start working on the exercise, and then we can take them in Slack, also take them here. I don't know.
Yeah.
Okay.
I think that would be good.
It's just one slide that I have for the exercises. Let me see here. Close the chat. Okay. So I put a bit of code online. The URL is you see up here, cryptojeddah.org/space2021 #space.tar.bz2. And in that tar archive, you find, well, essentially two programming assignments, one to implement Lamport and one to implement Winternets. And they're in the files lamport.c and winternets.c, and you'll see that in those files it says to do implement. Together with this, there's a make file and there's some regression tests. So you actually have a test, you can implement them, you can type make, and in the test subdirectory, it will build a test Lamport and a test Winternets, and you can run them. And if they don't output anything, then it might be correct. It's somewhat tested. They could probably be more extensive testing. What you will also see is that there is an implementation of random bytes included. So if you need any random bytes, you can just call the function random bytes, where the first argument is a pointer to the buffer that you want to fill, and the second argument is the number of bytes that you would like to receive. There's also an implementation of shake256. So you don't need to implement the hash function. You can just use the implementation of shake256 that there is. For Winternets, I suggest that we stick to the parameters that I showed. So we use w equals 16, so we chop the message into 4-bit chunks. That's actually pretty much the easiest. And you will also see in a file winternets.h, there's already some macros set that basically fix all of the values that you should care about. Now that's what I'm suggesting we do in the next, I don't know, something like maybe we do a bit of a break now, and then we do this maybe for 1.5 hours. And I'll be on Slack. I'll also stay online here on Zoom, maybe muted, and then you can also ask questions here. I'll try to clarify that. Afterwards, and not part of today, if you want to continue with this, then the obvious next step would be to implement stateful Merkle signatures based on the Winternets signatures that you have from part 2. I would use tree height 10, so that's not a multi-tree super fancy thing. I would also not use bit masks or something. Thank you very much for posting the link in the chat. You can then implement a forward secure version. If you want to go even beyond that, you can implement configurable trade-offs between state size and speed. So do this BDS traversal algorithm, look at that paper. But yeah, so that's not the plan for today. It's just some ideas of how to continue after this tutorial. Just shall we, I don't know, do 10-minute or 15-minute break, and then we start?
We can do that. Peter, there's a question in the chat. It's from Oliver.
But that is just the link that I posted here, right? So that everybody has the link.
No, there's a question.
In the chat here. No. How do hash-based signatures compare to lattice-based signatures? Code size, key size, signing speed. Okay. Great. Thank you very much for that question. So hash-based signatures. So the key size is where they're really doing better. So with these tweakable hash functions and everything, the public key is, I think, 32 or 64 bytes. So it's really small public key. So that's pretty all right. Signing speed, it very much depends on if you have stateful or stateless signatures, and it depends on the amount of state that you're keeping around if you have stateful signatures. So if you're using the stateless signatures, so the ones that are submitted to the NIST competition, then signature sizes are considerably bigger than lattice-based schemes, and signing speed is considerably slower than lattice-based schemes. Then again, you can say that they're quite a bit more conservative because there's not much computational assumption in there, except for the assumption that we have a good hash function. But that's something that also pretty much any other signature scheme or that really any other signature scheme also assumes. There may be some subtleties in what properties exactly you're assuming from a hash function, but well, if we're okay with modeling hash functions as random oracles, then we're definitely on the very conservative side with hash-based signatures. So I would see them as less efficient than lattice-based signatures, but a more conservative choice for applications that maybe don't need very low latency signing and can live with somewhat bigger signatures. What's maybe worth mentioning is that if you can customize signatures, so you don't need to stick to some standard or something like this, then, and you care about speed, but throughput rather than latency, then hash-based signatures give you an extremely nice way of batch signing, where you, for example, say, well, I'm always generating 1024 signatures at the same time, which means that you're generating, like you pick a construction where at the bottom you have a tree of height 10, a Merkle tree. You generate that tree once, and then you just use all of the leaf nodes one by one. So then the asymptotic cost for compute, and then on top of that, you put some hypertree construction, whatever. But then the cost is asymptotically just the cost of a one-time signature. Because while you need to compute the signing all the way up through the hypertree, that you need to do once, but then the other 1023 signatures, you basically get for free. You keep the small tree of height 10 in memory. You just need to pick up the authentication paths, combine this. So you can do some extremely efficient things if you're willing to customize hash-based signatures exactly to your application.
So we take a break for about 10 minutes, and yeah, so at least in India, that could be back at 6:20. That's roughly 10 minutes from now.
All right, then I'll also quickly grab a coffee, and I'll be back in a little less than 10 minutes.
Yeah.
Okay, thanks.
Thanks.
Okay, so I hope that the screen share that I have is big enough for everyone to read. So just to give you an idea of what the,
Yeah, it would help if you increase the font a little bit.
Increase the font. I think I could do that. Let me see. Settings. 24, like that?
Yes, that's great.
Okay, perfect. So when you download this tar ball that was linked on the slides, and that is now also linked in Slack. By the way, I also now put a link to the slides in Slack, so you can also find slides with all information. Then, well, you unpack the tar ball, and then what you get is something that looks like this. So you have Lamport, you have Winternits, you have Shake256 available for hashing. You have this random byte implementation and a makefile. And when you start to work, say, I would recommend to start on Lamport. Then in lamport.c, it looks like this. So you have this crypto one-time signature key pair or one-time sign key pair, where you will have to somehow generate 512 random 32-bit value, 32-byte values, 256-bit values, and then store them in a secret key, and you will have to hash them all and put them into the public key. They can all, everybody's joining. Then there's the signing here, where you get the message. You get a pointer to the 256-bit 32-byte message, and well, you need to scan through the bits, and for each bit reveal the correct thing. So you need to copy the right thing from the secret key to the signature, and well, the message length is actually, sorry, the message length is actually, so you need to sign a message hash, so you get an arbitrarily long message. And then in the end, you have the verification where, well, you need to take the signature components and hash them and compare to the public key. When you can build this by just typing make, and make will build all of this, and at the moment spill out a whole lot of warnings because parameters aren't being used, and there's no return value and nothing. So, but it does build something. It builds a test, and if you want to run the test, then you can run test lamport, and it will complain that the signature doesn't verify because we're not actually generating any key pairs or computing any signature. So the task would be to make sure that this test passes. And then same thing for Winternets. Maybe good to take a quick look at random bytes. So this is the random bytes header. So as you can see, the function random bytes receives two arguments, one being the pointer to the buffer that you want to fill with random bytes, and then the second one being the length of the buffer, or the amount of bytes that you want to fill into the buffer. And then when we look at shake, you see that there is this shake function which, well, you feed in some. I need to move my overview here. So you have some input, you have a certain length of the input in bytes, and you produce a certain output with a certain length of output in bytes. Now, in the case of lamport, all of the inputs and the outputs will have 32 bytes in length. So that's maybe something to keep in mind. Yeah, and with this, I'll let you get started. I will be in the Slack channel. I will also be here. I'll probably mute myself, but if you have questions, just feel free to ask wherever, and well, see if you can get first lamport to work. Maybe when you get lamport to work before you move to Winternets, you can also ping me in Slack or something, so that I have an idea of where we are and if it's even realistic that we get both things solved. But yeah, okay. So have fun, and I'm around.
Sumit, just hold on.
right. It's maybe a kind of good moment to start taking a look at the solution or a solution to the programming exercise. Of course, I can't tell how many people are actually still there, and I can't really tell how far you are. I saw that at least one person solved the first part of the exercise. So yeah, let me present a little bit how I would solve this, or how I did solve this. So basically, the first part of the assignment was to implement the Lamport signature, and when we do this, what we first need to do in the key generation is we need 512 chunks of 32 random bytes each. And we can just do that as one large continuous stream of random bytes. So basically, we're just saying, well, as the secret key, give us crypto OTS secret key bytes, and just read them from wherever random bytes reads its random bytes from. That's really easy. And now we want to sign messages, or we want to sign hashes of messages that have 256 bits. So we want to look at these hashes. And for each bit, we need 2 values. So how many bits do we have? Well, we have crypto OTS hash bytes times 8 bits. So that means we need crypto OTS hash bytes times 16 chunks. So we need to now take these the secret bytes and hash them individually. And the way that I'm doing this here is I'm taking well, secret key as input, and I'm always reading crypto OTS hash bytes, so 32 bytes, and I'm writing this to the output. And then I'm moving the pointers ahead. So I'm just saying, well, now please point to the next chunk of input and point to the next chunk of output. So I'm increasing the byte pointers by crypto OTS hash bytes. That's it. By the way, if there's any questions at any point, if anything is unclear, please interrupt me, poke me about this. So in the signing part, what we need to do is, well, we need to reveal chunks of the secret key. And in order to do this, well, we scan through all of the bits of the message. And we do this by, well, scanning through the bytes of the message. And then, so in one loop, that's the loop over I, which goes over 32 bytes of the, well, message or hash. I should first say, so I'm not doing this collision resistant thing. So we're first just taking the message and we're hashing it to H. So we're just signing a message hash here. And yeah, so then I'm iterating through the bytes of that hash, and then I'm iterating through the bits of that hash, or the bits of each byte. And we get the bits by saying, well, we take the current byte that we're at, and we're shifting it to the right by position J, and then we end with 1. And then we just say, well, what we copy from the secret key to the signature, and we copy from position secret key with an plus bit times hash bytes. So either we just copy from secret key, or we copy from secret key plus 32, depending on, well, if the bit is 0 or 1. Or we copy crypto OTS hash bytes, so 32 bytes. And then we say, well, we increase our pointer to the signature by 32, and we increase our pointer to the secret key by 64. So basically, that means we're pointing to the next chunk of signature, and we're pointing to the next chunk of secret key. So we always need to, well, move over double the distance in the secret key. And that's essentially it. Now we just need to verify. And we're verifying by first of all computing the message hash, so we get this H. And then we're again iterating through all of the bytes, we're iterating through all of the bits. And we're extracting the current bit of the message hash that we want to look at. And now we're taking the current chunk of signature and we're hashing it to something called P. There's a question. On line 32. Regarding endiness. Yeah, so it doesn't matter what I'm doing in terms of endiness as long as I'm doing the same thing on both sides. This is, at the moment, this is running on the same machine anyway. But also, I'm only working with byte arrays, so there isn't a real endiness issue in terms of, so if I'm running the same code on a big endian machine because I'm not using any 32 or 64-bit integers that would be stored differently, there is no no real issue here. But of course, I need to figure out in which order I'm treating the bits and the bytes. So of course, I could go through the bytes in a different order, or I could go through the bits within one byte in a different order. And while that needs to be consistent between all the implementations. But running this on a big endian machine, if I'm not completely mistaken, like just the verification would still be verifying a signature that was generated on a little endian machine. Okay, so we're computing the message hash. We're hashing the current signature component that we're looking at. And now we're comparing it to the chunk of public key. And again, we're just doing a mem compare here. Earlier we did a mem copy, now we're doing a mem compare of that value that we computed. And we compare it with public key plus either 0 or public key plus 32, depending on what the value of the bit is. And if that mem compare returns anything that is different from 0, then we return -1. And then we just point to the next chunk of signature, and we point to the next chunk of public key, which is just the same as we did for sign. So that's the whole lamport scheme. And when I build this, you will see that there's no output, which means that everything is fine. Are there any questions about this? If there are any questions and I'm not quick enough now or something, or too quick, then maybe just post them in the Slack channel, and then I'll. There's one question popping up here. Okay. There's another question. Shoot.
Okay. Can you hear me?
Yeah, I can hear you.
Perfect. I was just wondering, from an implementation point of view, would it make sense to make it a two-dimensional array with respect to performance? Because now everything is in one direction, actually one dimension, and I'm struggling with the 4 bytes per value or per random number. So would it make sense to go to two-dimensional arrays, or would that pay too much in performance?
So if you're doing a two-dimensional array simply on the stack, then that will be flattened by C. So this is all at compile time resolved. So if you find that easier to read, then that won't make any difference. If you're creating a two-dimensional array by creating an array of pointers and then dereferencing those pointers in the array, that would, I mean, this is not really optimized code anyway. So I find it most readable like this, because I'm imagining secret keys and public keys simply as, well, just one long stream that you chop into blocks, right? And then to me, it doesn't feel like, so two-dimensional array would for me be something where I think about it as a matrix, and somehow here I don't think about it as a matrix. But I mean, you can think about it like that. There's nothing substantially wrong with it. So yeah, you can totally write the code with two-dimensional arrays. But if you just write something of the form secret key is an array of bytes of length 512 and then bracket 32, right? So bracket 512 bracket 32. The compiler will flatten that to just a continuous chunk in memory, and all of the indices will be resolved at compile time, so that there isn't any issue with performance.
Okay, thank you very much.
Sure. Okay, then I'll briefly present the Winternet solution. So what we need to do for Winternets is we need randomness. We need to initialize our 67 bottom strings for these chains, right? So we're basically just saying, well, again, we're just reading these bytes. And now we need to take each chain individually, which means, well, we have this what's L, that's 67. So we go through 67 chains. And we need to hash them up. So we're just taking whatever we have in the secret key, we put it in the public key, copy that. So that would be, well, R0, but then we're just hashing upwards and we're just overwriting constantly the current value. This is not doing anything fancy with bit masks or anything. It's just straightforwardly hashing up. So we're just taking our current value at the public key and hash 32 bytes and store it again where we had it before. And then we just move our public key pointer ahead, we move our secret key pointer ahead by 32, and then we're just pointing to the next chain, basically. So that's the whole key generation. I should probably have this log W. I should have that what's W if encapsulation also in the OTS key pair. The key pair also assumes that. But now in signing, what we do is, again, well, we compute a message hash. So that's the first thing. That's the thing that we're signing. And now we're doing something like what we computed before. So we go through our chains. So now we need to first go through first 64 chains, which each chain corresponds to one nibble of message. And what we did in key generation is we copied from the secret key to the public key. Now we copy from the secret key to the signature, and we're just hashing forward and keep overwriting that value. And how long do we need to do this? Well, we take our hash byte at position I12, and we AND that with 0xf. So that would mean we take the low 4 bits of a byte, and then we use that as the loop length for this forward hashing. And in the hashing, well, we just hash from signature to signature 32 bytes, and that's it. Now our checksum was introduced up here as the maximum possible value, which is what's L times what's W minus 1. So that would be the 960. And we now subtract T from the checksum. So that is basically on the fly computing this this checksum sum. So the 960 minus the sum over all of the MI, or in this case it's called T. We just keep updating this. And then, well, we point to the next chunk of signature, we point to the next chunk of secret key. And then we do this for the upper half of that byte that we're currently looking at. So we're now shifting that byte to the right by 4, and that gives us the upper half. And then again, we're doing the same thing, which we compute this value of T, we do the chain of length T, and then we subtract from the checksum. So that's all of it. And then we need to compute the same thing for the remaining few chains of the checksum. And well, what we're doing here is just the same as before. We're going through all of the checksum things where we take the current checksum, we compute it with 0xf. So we take the least significant. We use that as an index for the chain. We hash forward in the chain. We then shift the checksum to the right by 4, so that in the next loop iteration, we take the next 4 bits and we move the signature and the secret key pointers to the next respective chain. That's all of signing. And then finally, what we do in verification, again, we compute the message hash, and now we need to finish the message. We need to finish the chains all the way up to the top. So again, we go through the first 64 chains. We compute the current value of the message hash, so the current chunk of 4 bits. And now we just compute the chain from the maximum value. Well, we go from T to that maximum value. So that is exactly finishing the chain. And before that, well, we copy from the signature to the public key and then hash all the way up to the public key. And then we subtract the checksum T from the checksum, and we increase the pointers to signature and public key. So notice here that the verification actually computes the public key, right? So this is what I said, this reconstruction, that verification recomputes the public key. We do the same thing with the next nibble by just taking the upper 4 bits of the byte, so just as before, and then at the end we do the same thing for the checksum, and then we return 0. So this is looks a bit of a weird verification routine here, but because it doesn't actually return true or false, it returns the public key. So now the task of the test is to then compare that public key to the original, or this returned public key to the original public key. Or if you're using it in a Merkle setting, and this is why this is doing this. So if you want to use that code now to construct multiple time signature scheme using a Merkle tree, then you can just do this, and you don't have to include the public key in the signature. And again, when we build this here, make team, make test winternets. It doesn't output anything, so everything works. So now I think was there just a question? There's again a question about endianness. So I believe this code is completely independent of any endianness issues. So I think there would be zero effort to make this endianness independent because we're only working with byte arrays. There is no endianness issue. I did not test this though. So maybe I'm missing something, but I don't think there is any particular issue. You do get an issue with endianness when you implement the Merkle scheme, because for the Merkle scheme, for example, you need to write the index into the signature. And you would usually keep the index as an integer sitting around. And when you're writing it, well, to your secret key, that's a local decision. But when you write it to the signature, you need to take care of the encoding. But all of this here is just byte arrays. There's no issues with endianness. Any other questions? Please, if there's more questions coming up, if people still want to work on the assignment, just keep posting in Slack. I will have to sort of rush off now because I need to be in a PhD defense of one of my PhD students in a bit. But well, for me, I thank you all very much for your attention and for actually going for this assignment and trying to implement this and asking questions. That was definitely great. And yeah, I would say that concludes the tutorial, at least from my side. Chester, I don't know if you're still around, if you want to say something.
Yes, Peter, thanks a lot for this wonderful tutorial, especially the assignment. So this was actually very interesting. So on behalf of the Space Committee and the organization, I'd like to thank Peter for this tutorial. Thanks, Peter, and thank you all for joining and staying for the entire tutorial and also trying the assignment. And many of you did try it. The session will, I think the next session is a paper session. So that will continue as in the program. So thanks everyone and have a good day. Bye.
Thank you all so much. And hopefully see you soon in some nice place in this world. Bye.